In this session, we'll look at the central limit theorem. That will be the most important result of the course. So why do we want to do this? Well, it's because normal distributions show up everywhere in real life. So if I did a histogram of the heights of first students and nums, that would approximate a bell curve. It would look like the information had come to us from a normal distribution. If we looked at weights of first students, again, I think it would likely approximate a bell curve. If I did the results of 1,000 random walks, terminating after 2,397 steps, and you looked at where you ended up. So random walk would have the walker at each tick of the clock decides randomly with 50% probability to take one step to the left and one step to the right. So now we keep track of where the walker ends after 2,397 steps. And we have 1,000 random walkers. Okay. And what happens? The results look like it. Okay, so where are all these bell curves coming from? What's the underlying idea which is giving us bell curves of right, so we have a theorem which is called the central limit theorem. So if we have x1, x2, and so on, it's a sequence of independent, identically distributed random variables, and they have, sorry, I shouldn't say mean here, say expectation mu and variance sigma squared, each one of them, because they're identical. And then we take a sample. What would the if we take n of them, what would their mean be? So sorry, what would their expectation be? Their expectation would be n times mu. And what would their variance be? Their variance would be n times sigma squared. So their standard deviation would be sigma root n. Okay, so now if I take a new random variable, x1 plus x2 up to xn, we take n of them, any of these identically independent, identically distributed random variables. We take a new random variable, which is their sum. And then the distribution of this sum, okay, and then what do? I normalize it. I subtract off the expectation of the sum, and I divide by the standard deviation of the sum. Central limit theorem says basically that this tends to the standard normal as n goes to infinity. So the probability that for some a, no, this should be a positive a. So for some positive real number a, the probability, no, so it doesn't have to. So, for some a, which could be some real number n between minus infinity and positive infinity, the probability of the standardized variable, probability that is less than or equal to a, goes as the CDF for the standard normal as n goes to infinity. Or another way of looking at it is that the probability of this, that the value of this standardized variable lies between a and b, tends to the integral from a to b for the standard normal, right? the probability that the standard normal lies between A and B. So, right. So as I said, if we have a sum of xi's from 1 to n, and if these are independent, identically distributed random variables with the same mu and the same standard deviation sigma, and then we take their sum, then that's going to be approximately normal, with mu of the sum being n times mu, and sigma of the sum, standard deviation of the sum, being root n sigma. Okay, so let's take an example. So we have the average height, let's say, just making the numbers up here, okay? Let's say that the average height of adult women in the world is 64 inches. And it's approximately normally distributed with the standard deviation of 3 inches. Approximately what percentage of women have heights of more than 67 inches? Okay, so that's so it's 64 inches, and the standard deviation is 3 inches. So that means what's the probability that heights are more than one standard deviation, more than one standard deviation larger than the mean, which is 64 inches. So that would be the CDF evaluated at one standard deviation, right? So probability the height is bigger than 67 is a probability that the standard normal takes a value bigger than 1. That's 1 minus the probability that the standard normal takes a value less than or equal to 1. So that's 1 minus from your CDF table, so-called Z table, you would get 1 minus 0.841. That's 0.1587. So approximately 16% women would have heights greater than 67 inches if what we were saying is true. Okay, let's try another one. But notice here again, we don't know what the underlying distribution is. We're making an assumption that heights are independent, and whatever distribution it is, it's the same for everyone. Okay, so there's a true-false test. It has 48 questions. What's the exact probability of getting 30 or more questions correct just by flipping a coin and writing true if you get it, T, and false if we get an H? Okay. Well, now so probably getting 30 or more. So we'll assume that okay, so you've got all these xi's, right? So x1 is the result of you got this right or this wrong. X1 for the first question, X2 for the next question. Okay. All right, so the probability that x is greater than equal to 29, if we just use the binomial, okay. So probability that x is bigger than 29 is 1 minus the probability that x is less than or equal to 29. And then this is going to be by the binomial distribution. You get 0.055714. That's an exact answer. Okay. Now let's approximate using the central limit. So we've got x. We have these random variables xi 1 through 48. Xi equals 1 if the ith question is answered correctly. Xi equals 0 if the ith question is answered correctly. So the sum of the xi's is this number that we're looking for. The xi are independent because the point flips are independent. Okay, and each xi has the same mu. It's 1/2. And the variance, we can work that out to be 1/4. Okay. So the xi are independent. The sum of the xi has expectation n mu, and it has variance n squared, and standard deviation root n sigma. Then the probability that s is less than or equal to 29 is the probability of, you have to normalize this s, right? So s minus n mu over root n sigma is less than or equal to, and you have to, whatever you did to s, you have to do to the 29 here, right? So you have 29 minus n mu over root n sigma. So then this normalized variable, that's the probability that the normalized variable is less than or equal to 29 minus 48, right? There were 48 questions, times the mu. Each one had each of the xi's had a mu equals 1/2, and root n is root of 48, and the sigma was 1/2. So this is the probability. This is approximately equal. Now we invoke the central limit theorem because we meet all the conditions. So this means that this is approximately equal to the probability that the standard normal is less than or equal to this thing on the right, works out to 1.4434. And then if I check my Z table, I get 0.9255. Okay, then the probability of getting more than 29 correct would be approximated as 1 minus 0.0745. Okay. Try another one. Suppose that the PDC serves 4,000 meals a day. 20% of those include dessert. Give a range of the number of desserts ordered in a day so that there's a 95% chance that the actual number is in that range. Okay. So let's see. 4,000 meals a day, 20% of those include dessert. And you should note that 2 standard deviations on either side of the mean gives us about 95% of the area under the curve. So we can take 4,000 random variables xi. That takes the value 1 if the ith meal contains a dessert, 0 if it doesn't. If I take the sum of the xi's, then that would give me the number of desserts, right? And yeah, okay. We're assuming that everyone is ordering their meals independently of each other. That may not always be the case. I might be influenced by my friend next to me or something. But, you know, we were doing approximations. So let's assume that everybody is independently minded and decisions are being made independently and according to the same random variable. We don't understand what the underlying random variable is. Okay, what is the mu and the sigma of the underlying random variable? Well, mu is the expectation of xi, and that's equal to, what are the possibilities for mu? For xi, either 0 or 1. Did not get a dessert or got a dessert. Okay. Did not get a dessert with probability 80%, and did get a dessert with probability 20%. That gives me a mu of 0.2. Okay, what's the variance? The variance is the expectation of x squared minus mu squared. Okay, so what are the x squares? Those are either 0 squared or 1 squared. 0 and 1 are the possibilities for xi. And the probability of getting a 0 is 0.8, and the probability of getting a 1 is 0.2. And that's my expectation of x squared, and I have to subtract off the square of the expectation, and the expectation was that was 0.2. So I do that calculation, I get 0.2. Okay, so the expectation of S is n times mu, or 4,000, so it's 800. And the variance is n times sigma squared, so 4,000 times sigma squared, which gives us the variance for S is equal to 25.30. Okay. So 2 sigmas would be 50.60. So 2 sigmas on either side of the expectation should give us about 95% of the area under the bell curve. Okay. So that means between 700, the actual number of desserts required, that will be between 749 to 851 with a 95% probability. So when we, if we have the if we have the records from the PDC, going back through them, we get this information that 20% of the time people want it served. But of course, that's an average. Sometimes they want more of them will want a dessert, less. I don't want to make too many desserts, and I don't want to make too few and disappoint people. So I might decide to err on the side of caution. I might make, say, 850 desserts in a given day, and there's a 95% chance that I'll be okay. All right, so that was the central limit theorem, and as I said, it makes an assertion about why normal distributions show up so much, and it really is used all the time in practice.